Okay, we're going to continue part 2, unit 5 on thermoplastics. So engineering thermoplastics are not regular thermoplastics. Okay, they're different because something is engineered into the regular thermoplastics, and we have 4 of them. So these are typical engineering thermoplastic that we use. Acetals, your fluoroplastics, and you have your polyamides, and we call it nylon, very popular with the girls, polycarbonate. Okay, so acetals, they're polymers, and we engineer formaldehyde, so polyoxymethylene, POM. They're very strong and strongest, engineering thermoplastic, and stiffest. They're excellent fatigue resistance. Okay, they can resist fatigue or some form of stress or load. They are dimensionally stable and exceptionally solvent resistant. They also have high heat resistance, and they have low friction coefficients. I want you to just go lightly on acetals, alright? You don't really have to remember everything. If you know like what is acetal, at least to come up with formaldehyde is in it, I'm okay with it. Okay, nobody can remember all of them, so just try to pay attention. And probably you might have to read again and again, but don't stress yourself so hard. When you go to work, if you get into purchasing or supply chain, okay, material handling, you will have your handbook. Okay, everybody need a handbook. And you have the data, right, for all these that you have to deal with every day. So it's a headache. Anyway, so fluoroplastics, they are fluorocarbon polymers. Okay, here the engineering products right here, fluorocarbon is in it. They're inert, meaning that it's not reacting anything to chemical. They have high temperature resistance and low friction coefficients. They have excellent dielectric properties, and they have poor mechanical properties. The feel is kind of waxy for fluoroplastics. Okay. The next one is PTFE. So that's a poly for P and tetra for T and fluoro for F and your ethylene, which is your thermoplastics. So PT, okay, F and then E. So what do we engineer? We engineer TL, tetrafluoro, okay? This form of tetride 4, okay, and then you have fluorine 4, then we put into the ethylene and make it a polymer, yeah? So it's a very most common fluoroplastics is a PTFE, and in common word, Teflon, yeah? So if you think about Teflon, you want to remember your pan, yeah, in your kitchen. So the monomer looks like that. So instead of 4H, we have 4 fluoride, okay, here in it. So you can say like fluorine atom, 4 of them forming a fluoride with 2 carbon. So what are we using? PTFE, we're using them to make tape sheets, Teflon pans, coatings, right, and here furniture materials. So some of the furniture, even though they look like wood because we paint or decorate it, they're not wood, right? They're just plastic. Polyamides, commonly known as nylons, the structure like this, a little more complicated, yeah. They have like 1, 2, 3, 4, 5, 6 carbon atoms. That's just a monomer, yeah. And then you're gonna link all of that monomer into a very, very long molecular chain. So we have many different types of polyamides or nylons, and that type Okay, these types are determined by the number of these couplings, right, in the monomer. A typical one, again, has 6 of them, yeah? So when you take a look at their properties, they have excellent mechanical properties, but they can be affected by moisture. So moisture is enemy to nylon. They are resistant to fatigue or stress or load and creep. And they have high impact strength, but low friction coefficient, and a high wear or abrasion resistance. Okay. Polycarbonate. When you take a look at the structure of polycarbonate, this is a small monomer, the very large complex molecule. Yeah, these are, each one of them has a little carbon right in it. So it has 1, 2, 3, 4, 6 carbon here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons right in there. Yeah, with 2 oxygen and 6 hydrogen. So that's a big, large, complex molecule. So if you think about appearance, outside clear and transparent, properties strong and rigid, chemical strength is close to crystalline nylon and acetal. They have exceptionally high impact resistance. They have good electrical properties and good thermal stability and a good creep resistance. We've been seeing creep 2 times. We're going to talk about that, what that is here. So properties, mechanical properties of thermoplastics. So they have tensile behavior, viscoelasticity, and they have glass transition. So these are the major properties for thermoplastics. Tensile, different strength, yeah. Viscoelasticity is one of the plasticity type. We have linear, we have non-linear, and then we have visco. We'll go into one by one. And the next one is the transition between hard and glossy and soft and rubbery, and there's a transition period, and we call the gloss transition. Okay, and just a region. So let's take a look at the strength and behavior or tensile behavior of thermoplastics. So when you look at the stress strain behavior, you can see the tension test is necessary, all right, to understand the tensile behavior. So we use it in the same way as we use for metallic materials. We use tension tests to test the metals. We will use the same test to test the plastic. Okay, so plastic differ from one another. And how do we differentiate the plastic? By looking at the modulus of elasticity, yield stress, and elongation before fracture. Okay, so when you take a look at this picture from the handout, it's showing you 2 tensile stress strain curves, right? One here, one there. So we have 2 thermoplastics. One is a polyvinyl chloride, your PVC, and the other one is a PS, which is your polystyrene. So you can see the deformation at various points of stress strain curve, similar to the metallic materials. So this is what you normally get, right, for stress strain behavior graph. And we call it curve. And these are just the deformation curves. You can see the polyvinyl is more deformation than the polystyrene. And the stress applied, and that's your pressure. Alright, some stress time 10 to the power 3, so that's pretty big, right? Stress. A big load, maybe. That's why it deformed. Now I'll get into material behavior, and we will take a look at steel and thermoplastic. So that's your steel and that's your thermoplastics. So the stress strain behavior for plastic is like that of the metals, and that it's true only when they are at room temperature in a short period of time. Okay, polymer properties, they can change a lot and they can change significantly over time. Okay, so therefore only a short period of time you can see the metal and the plastics, right? Stress strain behavior are similar, and again, it's got to be at the room temperature. Okay, but over time, plastic is going to behave differently. Yeah, metal won't. Viscoelasticity, again, polymer properties, they depend on time a great deal. Okay, highly dependent on time. So when you study the material science, material response, when you look at it, polymer falls between elastic solids, example steel, and a viscous fluid, example oil. Okay, so we have steel and we have oil, and your polymer is in between them. So when you think about the mechanical behavior of polymers, they are viscoelastic because they have certain chemical responses like elastic solids and viscous fluids. Okay? So here are polymers, and here you can see that's a viscous fluid, right? So you can see it has more space than that. Yeah. And I want students to have a connection between the structure inside and what you can see outside. So when you take a look at something is oily or liquid or fluid, okay, that means that inside they've got more space. That's why it can be flexible, right? The material, you can look so flexibility. They can't go off. They're still together. That's why you can see them as liquid, right? Bonded, still bonded, but not as tight space as in solids. Okay, in solids they can't move too much because there's not so much space in between the structures. Yeah. So this is your strain-time relationships of constant stress. So we have my A and B and C. So the very first one, okay, is your ideal elastic solid. We're looking at solid, and we're putting this behavior or relationship between the strain and the time. Okay. Again for solid, and the graph looks like this. The viscous solid, stress, and the time. Okay. Here is the strain and the time. And here is a typical polymer. And this is your viscoelasticity. And you can see this is your strain, and this is your time. And you can't be able to make a lot of meaning out of it, right? But right now, since this is not engineering class, we're going to go light on this. And all you have to understand is when you take a look at it, how different the graph is between the strain and the time. Yeah, between the strain and the time, between the strain and the time. So when you pay attention to time 1, see how the solid just go up. Thus, the strain pretty high, and then plateau out to another period of time, right? In time 2, coming back down. And here, we're getting into the viscous solid, right? Ideal plateau and won't come back at time t. We're coming into polymer, dealing with plastics with viscous elasticity. Time 1 taking off, have a little bit of strain. Okay, we're going towards time 2, right? Still have the strain going up, see? And then come back down, and then continue irregularly. Yeah. But what it's telling you is there is strain, okay, for the plastics, right? For solid, there was strain, but then it comes back straight down. Viscous solid, you're gonna keep on going, okay, at that strain amount. Again, don't pay so much stress on it. Just understand and try to know if I give you this graph, you know that that's what. Either elastic, solid, yeah? Elastic go and have a strain and come back down. Ideal viscous won't come back down. Typical polymer go up, up, come back down, and then still going. Creep. Okay, so we saw creep 2 times. Creep resistant, what does it mean? The viscoelasticity of polymers have a 2 application, practical, right? Application issue. So creep is an issue, application issue or problem, something bad in application. So what's that? 2 of them, practical application issue. One of them is creep and the other one is stress relaxation. So creep is just a deformation phenomenon, and that happens when constant stress or load, we're going to apply that stress or load to a polymer. Yeah. Creep causes extensive deformation on the parts, meaning like it's going to deshape your plastic if you put some heavy load on it. Okay. So this deformation can continue to increase with time. So the more the plastic got to carry the heavy load on it, the more deformation it's going to get over time. Yeah, and we call that creep. So when you go inside of the molecular structure, you're going to see that's before the creep, and this is after the creep. Yeah, see how it got pressed down. Stress relaxation, another application problem. So if a polymer or your plastic is deformed, and it's going to be held at some level of strain, yeah, and then your time is going to continue. So the plastic part is going to lose its loading capacity, okay? Because it's got to be holding something on it, and you have a deformation with it, so it can't, right? It can't give full loading capacity. So definitely stress relaxation, meaning like because of the stress, plastic is losing loading capacity, yeah? So here, creep and stress relaxation diagram. So you can see here, this is our time, okay, and we have a fixed load, okay, on it. And here you can see the permanent deformation happen because of that load over time, yeah. Stress relaxation going, time is going, and fixed strain is on it, and it's been held for some time, yeah. And you can see the permanent deformation, okay. This is your load, and your plastic is right here. As it's just telling you some sort of force, fixed load, and we gain permanent deformation because of that stress. Okay, we call that creep, and we call this relaxation. What's the difference? For stress relaxation, all right, that deformation happened and then held at some level of strain. Okay. Okay, thermoplastic, we have rigid thermoplastic and flexible thermoplastic. Rigid, common word glossy, we call it, even though it's plastic. See how it looks like glass? That is plastic at room temperature, of course. Flexible, we call it rubbery, okay, even though it is plastic. So for rigid thermoplastic, we have acrylics. So chemical term is polymethyl methacrylate, and you have your PS, your polystyrene. So rigid plastic become rubbery if you're going to heat it, okay, above certain temperature that they can't stand. So if you heat it up all the way up, the rigid plastic is going to become like that, flexible. For flexible, we have polybutadiene and we have polyethyl acrylate. So rubbery plastic become rigid if you cool it down to certain temperature, okay? But then the change from the rubbery state to the glassy state, we call that glass transition, meaning like the rubber is going to, all right, transform itself into plastic by cooling it down, yeah? So if somebody says what's glass transition, you know that the flexible or rubbery state of thermoplastic, alright, is going to change to the rigid glossy state, okay? And what's the method that we use? We cool it down. What's the important point? We gotta cool it down to certain temperature, yeah? And it depends on the material, of course. Alright, so get into glass transition. Glass transition temperature. We have different temperature right there in the table. So for any polymer, there's a temperature, and below that temperature, in a glossy state, above which it is a rubbery state, okay? So you will take a look at the glass transition temperature. Below that temperature, your thermoplastic is in glossy state. Above that temperature, it is in rubbery state. So below that is rigid, above that it is flexible. So the temperature is important. Why? Because we use it to select plastics for certain applications, okay? Because we're making many different kinds of products, and in order for us to choose the right plastic, we gotta deal with the temperature. So here we have PE, polyethylene, glass transition temperature changing from flexible to rigid is at minus 193. 14 for PP, minus 4 for PVF, 199 for PVC, and 212 for PS, okay? They're pretty low temperature right here. This is kind of a normal range, and that's pretty high, yeah? But then don't get confused, that is a temperature changing from flexible state into rigid for PVC, okay? That's very high temperature. Applications. You gotta know what we use. So the very first one is your polyolefins. So we have 1, 2, 3, 4, 5 polyolefins. And I'm not going to read everything for you here, yeah? It's just a waste of time. So you can read them. So polyethylene, we use them in packaging, film extrusion, coating, paper, wire, cable coating, injection molding parts, and then blah blah blah. Okay, polypropylene fibers, films, fabrics, covers. So I just want you to pay attention that even though we talk about thermoplastics, alright, we use in various applications, various products, right? Food packages, chemicals, solvents, food processing, medical products, labware, okay? We use in automobiles, incredible amount of plastic in your car. We use in our house, okay? So just read through from here to here. If you can give me like a couple of examples, I won't be asking more than 5. If I want to make it easy, I'll ask you like 3 or something. Let's stick to the questions, assignment questions, and that's fair for everybody. Okay, let's go. Polyolefins, another one is called the UHMW, HDPE. So anyway, so their properties, they have excellent chemical resistant, they have low friction, they have high strength. UHMW is your ultra high molecular weight, high density polyethylene, okay? It's just a polyolefin, okay, one of the polyolefins. But then it's an important polyolefin because we use it. So we made it into blow film or packaging, okay? And then we extrude, using extrusion molding into pressure pipes, sheets. We use them in truck bed liners and pond liners. We blow mold it, okay? into large shipping containers, the plastic containers, or not the metal one. Then we use gear slides, rollers, and all industrial parts. We use bearings for artificial replacement joints in the human knees and heels. So why this polyolefin is so important, because it's give you really high, right, tensile strength. And they're very chemical resistant. So here I write down, okay? So this is very important. See how it looks so solid and strong here? So this is your UHMW, HDPE, and we're using it here in your knee replacement, okay, joint bearings. Styrenic plastic, 3 of them. Your PS, same, and ABS plastic, where we use in various applications again, yeah, from food packaging, cosmetic, pharmaceuticals, in automobiles, TV housing, PVC tubing lamps, boat, swimming pool, recreational vehicles. Your ABS plastic we use in refrigerator, food storage compartment. So that's your ABS plastic. It's not the same as SAN or PS. Your luggage, your toys, your sporting goods. Your keyboard computer is your ABS plastic. Your computer housing is also ABS plastics. Yeah. But just read through it, please. Vinyl plastics, 2 of them, PVC and PVDC. PVC very strong, so therefore we use in building construction, window, packaging, bottle, boxes. PVDC we use in food wraps, okay, your plastic wraps, medical packagings for medicines, gas-resistant coatings and containers. Yeah. Application acrylics. They're important because they're resistant to long-term sunlight exposure. Yeah. So we use it in aircraft canopies, resistant to weathering. So we use in skylights, outdoor glazing, auto tail lights, dials. We use to make buttons, lighting applications. We use to make various knobs, machine covers, drug packagings, and food packagings. Okay. Application for engineering thermoplastics. So we have acetyls, fluoroplastics, your Teflon, your polyamides, nylons, and your polycarbonates. So for acetyls, we use them in place of metal because they're very strong. Yeah, we use in conveyor chains, automobile door handles, your pump parts, Teflon seals, tubing, small vessels. They're not limited to only what I listed here. Okay, there are many more. Teflon we use also for pans and housewares. Nylons, a textile. Your ladies, a hosiery here, fabric, home furnishing, carpeting. We use in machinery slides, alloy elements for other polymers, so and so. Continue. Yeah, this is supposed to be full stop. Polycarbonates are changed. So polycarbonates we use in place of metals and glass. We can make headlamps, auto signal lenses, tractor window frames, so on and so all the way. Yeah? We use for motorcycle helmets, photographic equipment, etc. Okay, polycarbonates. Just remember polycarbonates for refrigerator storage bins. So here's the example from your handout. So storage bin like this is really glossy, yeah? But they're not glass, they're actually plastics. So what's the chemical term is polycarbonates. Nylon. This is a nylon rod. So nylon in specific engineering application, we can use nylon, right, by fiber reinforcement. It's just a specific engineering means we're putting something into the polymer. So if we put like molybdenum disulfide, right, and we want to put it as a filler in the nylon matrix, so what we get is improved meant in wear, abrasion resistance, frictional characters, flex strength and stiffness and heat resistance. So if we're gonna put glass fibers into nylon, yeah, we can improve the tensile strength. See how it looks like metal now? And the heat distortion, impact strength get real high. So that's what we call fiber reinforcement, is meaning adding something, spiking something into the nylon structure. So we can increase the tensile strength of it. Okay, so glass fiber, we put it into nylon, and you can get a very, very strong, right, nylon material. And that's how nylon is used in specific engineering applications. Yeah. Plastic recycling, we have to recycle the plastic because you can burn, right? Even if we can burn the plastic, the things that come out, the gas emission coming out from that burn is no good for our air. So therefore, we gotta think about alternative way to recycle, you know? So plastic occupy about 20% of the landfill volume. It's really important to recycle and reuse it so we can decrease the solid waste, right? We can also increase the landfill area. But there is property change in the plastic recycling process, meaning like the plastic property can change in the recycling process. And there is a need to improve the properties of these recycled plastics, alright? So when you look at the recycled plastic, it doesn't look good like the new plastic, right? Synthetic plastic looks different. Like the recycled tissue paper and new tissue paper, they're not the same. So new plastic and the recycled plastic, right? They're not the same. So thermoplastic, you can remelt and then reprocess because it can go through many heat cycles. It's not like thermosetting. Thermosetting can go through only one heat cycle and it won't go back to the original shape. But thermoplastic, you can remelt, reprocess. Thermoset or thermosetting plastic cannot be reprocessed, right? So we gotta sort thermoplastic and thermoset when we do recycle programs. So recycling programs, we have to separate the types of plastics. So sorting out the different plastics is going to give you a headache, right? Now you don't want to do that because the landfill smell is pretty bad in there. So only like the prisoners gotta go and work there. Homeless people can work there, right? And people who are desperate for money work there. People who have no qualification work there, you know? You don't want to go there and do that. Even that if you become like a supervisor or plant manager or GM or something, you still have to go and stick around. So to do the sorting, different types of plastic easily, we coat them. So resin means it's a plastic coat. And this Society of Plastic Industry, SPI, is doing that. Okay, they establish a code. And we're gonna sort different grades, right, of our plastics. Okay, so there are 7 codes. I mean, for this organization, okay, SPI. There are other codes, right? They go with their own crap. So code 1, PETE, is your plastic grade. This 1 right there, code 1, you can see 1 right there, that's just a recycle symbol. So PETE, meaning polyethylene, okay, terephthalate. So if you say code 1, you're going to put all PETE in that part, yeah? HDPE, your high density polyethylene, go to group 2, code 2, code 3 is V for your PVC, polyvinyl chloride, go there. Code 4, low density, okay, polyethylene. This is high density, this is low density, they're not the same. Code 5, your polypropylene, your polystyrene, and all others going into 7, yeah? Mostly the household trash goes straight into that category. So after we recycle and make maybe plastic bag again, and you look at the recycled plastic bag, it's just weird, yeah? So anyway, that's it for part 2.